Gravity is a fascinating topic, and one vital to life, but you should never put your trust in gravity because it will always let you down. Earth is huge, and we are but tiny dots on it, and yet it is but a pale blue dot compared to our galaxy, which in turn is but a speck compared to the universe, which likewise might be only a small corner of the wider cosmos and reality. So it tends to be almost inconceivable that this universe is empty of life besides us. Whether as a product of evolution or some grand design, it just feels like our solitary existence would be improbable. This is the core concept behind the Fermi Paradox, the big question of where all the aliens are. But when we say that, what we really mean is intelligent aliens. There could be alien life as close as Mars or Europa. Yet without a clever brain and the will to do so, that life can send us no radio signals, not launch any spaceship to escape from their homeworld's gravity well. And this will be our topic for today, gravity, and it's one that factors in at so many levels of the Fermi Paradox. From the formation of those galaxies to the lifetime of stars to if a planet can keep an atmosphere to if it can avoid keeping so much sea and sky that complex life can't emerge. If there is no land for photosynthetic organisms to evolve on, as it's all buried under water and the air is too thick for enough light to get through, then no spaceships are going to launch, for there shall be no one to build them. All of these and more might act as filters that make intelligent life less common. But we should begin with one commonly suggested filter related to gravity that probably doesn't work, and that's the idea that a planet might have too much gravity to allow spaceflight. Lots of gravity to fight means you need a bigger fuel to payload ratio, and also tends to imply more air to drag yourself through. Not only do we have alternatives that would still work well in higher gravity like space towers or mass drivers, but planets with much higher gravity than Earth shouldn't be good candidates for life anyway. Earth's orbital velocity is about 8 kilometers or 5 miles per second. Mars and Mercury are both just under half that, while Jupiter is 5 times higher than that. But we don't expect life down on Jupiter or Saturn, nor Uranus or Neptune, and they only double Earth's orbital velocity. What's more, bigger planets would tend to have collections of moons, making earlier space settlements easier in many ways. How big could a planet be and still have land life? We'll explore that more in depth throughout this episode. Earth is already the densest planet in our solar system, and thus has a higher orbital velocity than an equal mass lower density planet. As is, were we to Biggie size Earth to twice its size, same density, that would be 8 times the mass and double the surface gravity, and double the orbital velocity. This would be hard to do with chemical rockets since getting up to twice the speed takes a lot more than twice the fuel, more like 4 or 7 times the fuel, depending on what you were using, and meaning a spaceship that had been 90% fuel, 10% ship, and payload now needs to be 97.5 to 98.6% fuel, meaning what ship used to let you carry 10 tons to orbit now lets you do 1.4 to 2.5 tons, and that mass has to include the actual ship too, not just the payload and crew. Nonetheless, it would be possible, and again we have alternative means of getting to space besides chemical fuels. I also don't think that planet would allow surface life, but even in the smaller case, were we just to double the mass and keep the density the same, its surface gravity would only be 26% higher, and its low orbital velocity likewise 26% higher, 10 kilometers or 5 miles per second. 1.26 is the cube root of 2 incidentally. Mass and thus total gravity will rise with the cube of radius, and gravitational force will fall off with the square of radius. Compact objects of high density are harder to get away from than wide objects even of greater mass, hence why Saturn, the lowest density planet, is almost 100 times more massive than Earth but only has a low orbital velocity about thrice what we have. Alternatively, a dense and massive object like a white dwarf or neutron star is virtually impossible to escape from, and a black hole totally impossible once you get inside its event horizon, which is close enough that the escape velocity is light speed. Note that we've been saying orbital velocity to mean just over the surface where you're just clearing the air, or mountains for airless worlds. Escape velocity is usually a decent bit higher, but can be added slowly at that point, such as by hyper-efficient ion drives. And in very thick air cases, you might be able to float balloons up high to assist in launch. So it should be doable any place life can plausibly form, using chemistry anyway. Robert Ford's classic novel Dragon's Egg speculates about life on the surface of a neutron star, and instead of moving kilometers per second to get into orbit of one like your typical planet, you need to be moving nearer light speed, tens of thousands of kilometers per second. As great as that book is, I find it implausible that life would evolve on any stellar remnant, and I would be confident saying that if it did, it isn't ever escaping that birth world or birth star, as even impossibly strong hypothetical materials like magmatter probably couldn't form a space elevator there, and even an antimatter-powered ship couldn't get near the surface of one without having its magnetic bottles torn asunder by the field there. I suppose we might contemplate them using a laser to carve a nearby asteroid into a basic self-replicating machine that could build more of itself, and eventually a place you could digitally beam data to, like copies of your brain, to teleport people off the neutron star. Otherwise, you're stuck there. That seems nigh impossible, but it could work, and they probably can come up with something better than I did in a couple minutes of contemplation. Antimatter is the only known fuel that could handle the escape velocity from stellar remnants, and it relies on storing it separate from normal matter by careful magnetic containment, and magnetic fields are essentially impossible to completely block out. So antimatter storage doesn't do well anywhere where you either need to accelerate fast, shaking the bottle of super nitroglycerin so to speak, or where strong and varying magnetic fields exist, which is true of all stars but especially true of dense stellar remnants. Gravity is a very strong force, but ironically also the weakest, and by a long measure. The equations for gravity and for electric attraction or repulsion are identical, except we replace mass with electric charge and switch out the gravitational constant for Coulomb's constant. Both act as inverse square forces, weakening quickly over distance. But the electromagnetic force between two protons, pushing them apart, is a trillion times stronger than their gravitational force pulling them together. That's why hydrogen fusion, ramming two protons together, is so hard. But the key thing there is that the force is repulsive, and there's also an attractive force. A proton and electron pull on each other as hard as a proton and proton shove apart. And indeed the ratio of force is even more unbalanced here, as electrons are a couple thousand times less massive than a proton. The electromagnetic force between two electrons, shoving each other apart, is 4.16 times 10 to the 42nd times stronger than the gravity between them, or 4.16 million trillion times stronger. So protons are hard to push together for fusion, but cramming electrons together is even harder, all the more so from the Pauli exclusion principle. So this is what keeps white dwarf stars from collapsing further. Once they get enough gravity together, they can override even this, leaving you a star made only of neutronic matter. There are other forces, the nuclear forces, that are of similar strength to electromagnetism and vastly stronger than gravity, but they also have a repulsive and attractive form. Gravity does not. Although anti-gravity is not off the table, and gravity might have some weird connections to both dark energy, Hubble expansion, and time itself. It is very unlike other forces, being just attractive and trillions of times weaker than them, but it was the first force we discovered. So saying isn't a real force, as some do, always seems off to me, instead implying the other newer ones are different, not it, the original. How gravity works is fascinating and poorly understood, and we'll be exploring technologies depending on it more this winter as we look at gravitic spaceship propulsion, and then later more general gravity tech. But if gravity were a little bit higher, fusion in stars would happen a lot faster. The universe would also tend to be more compact and favor quicker star formation, so we would not have very good conditions for life. Our day-to-day existence is shaped by those other forces, It's what holds us together at the atomic and molecular level, and allows all our processes and power sources. But because they neutralize themselves, after you get to a certain scale, they no longer matter, and gravity runs everything. Just as above a certain scale, gravity is too weak and dark energy runs everything. In our recent look at the fine-tuned universe concept and the Fermi Paradox, I mentioned Stephen Baxter, who wrote a great book called Raft, which looks at a universe where gravity is 1 billion times stronger than here, still making it trillions upon trillions of times weaker than other forces, and he examines what the universe might be like. Baxter is a mathematician and engineer and focuses on writing hard sci-fi, and he is great with the technical details. We get no planets, just burned out husks of microstars a mile wide with semi-livable high gravity and new concepts like gravitic chemistry. Great read, and as we discussed there, even tiny changes in the physical constants could make life nigh impossible. My quick napkin math says that since the minimum zone for a red dwarf is about 60 to 80 times the mass of Jupiter, it would ignite as a star if gravity was that much stronger, 60 to 80 times. That stronger gravity also probably helps get a lot more clumping going on for more big objects in general. This in and of itself would tend to imply more planets and stars, and sooner in the universe's lifespan too. Indeed, given that normal stars would fuse a lot faster and die as supernovae a lot more often, rocky planet-forming elements should be around a lot more often too. By that same napkin math, if gravity was 60 to 80 times stronger, any star in this universe, transported to such a universe, would qualify as a supernova candidate, except maybe the very smallest red dwarfs. For a star to go supernova, it typically needs to meet specific mass and structural criteria, particularly during the core collapse supernova process. That mass limit, the Chandrasekhar limit, is almost half again our Sun's mass, but it's caused by that implosion event at the core of a more massive star, typically 8 to 10 times more massive than our Sun, or larger. There are too many other factors and unknown unknowns for even a cosmologist or particle physicist to answer confidently, and I'm just a regular physicist, but we can say that stellar lifetime tends to drop with roughly the cube of mass. This is not a hard and fast rule and varies by type, mass, and composition too, but it means a star that would live 10 billion years, like ours, if raised in mass by a factor of 10, would live 10 cubed or 1,000 times less, maybe 10 million years. This is because even though it has much more fuel than it used to, it burns it in its core far faster. It also gets a core full of those heavy fusion products while its outer layers remain mostly unused even when it explodes, while smaller and longer-lived stars tend to circulate their material around, so not only use their fuel slower, but get to use a larger percentage of it. I am hesitant to say this wouldn't allow life though, but I think what you have instead of our scenario is one in which early star formation, depending on how much stronger gravity was, passed as a faster phase. In a few trillion years, in our universe, a couple hundred times as long as life has now existed, star formation will start to slump off as available material for stars decreases. In the end, we'll have a lot more smaller stars, red dwarfs, as that will be about all that can form, and they live a very long time too. We often say this is the optimal time for life to evolve in should it not have already arisen, as rocky planets and longer-lived stars should be hyperabundant. In a universe with stronger gravity, this phase is going to happen faster, and in a generally dense type of galaxy where supernovae occur more frequently, planets can also be found by that gravity a decent way further out, given the increase in Hill sphere size. But no star lives long enough for planets to form, cool, and permit serious evolution, and those chemical and biological processes should not be accelerated by the rise in gravity. Again, they operate in a realm in which gravity isn't even a rounding error among other forces, even if made trillions of times stronger. So you probably can't have life till you end up with just red dwarfs, many of whom are probably in the brown dwarf or even gas giant range of mass, depending on if gravity were 10 times stronger or 100, but they still make heat and light the same way, so their fuel supply is a lot shorter. Planets need to be further away not to fall in, so to speak. Gravitational perturbations happen a lot easier when you're closer to an object, and only around very dim ones can they have enough time for life to evolve. Where that cutoff is in terms of how much stronger gravity needs to be to let life become impossible is hard to say, same for how much weaker it could be, but as we've seen, it can be very sensitive. Such universes, if they exist and can be reached, are still important to advanced civilizations as they become gold mines of resources and places where controlled fusion might be far easier, where gravity is stronger, or where megastructures of unimaginable scope might be built if gravity is yet weaker. Now, fundamentally, the Fermi Paradox is about conditions in our universe, and indeed really just our galactic supercluster and a few neighbors, since we cannot see most of the observable universe recently enough from light lag to see periods where life might have evolved and built spaceships and galactic empires. Either way, conditions in other universes, hypothetical or real, aren't normally much of a concern, but it is a good reminder how narrow the window for life might be, and again we discussed this and other physical constants changing for other possible universes in that fine-tuned universe episode. So too, if everybody figures out how to travel to such universes, they might opt for colonizing them over their native galaxy, which would obviously matter to the Fermi Paradox, though the sheer abundance of resources they would then have would seem to encourage them to spend some on saying hi to their original neighbors, given that there's not much reason for fighting them for territory either. So how gravity balances out with dark energy or universal expansion from galaxy formation if we tweak that constant or others doesn't really matter, as it is what it is for us, and it's our region of the cosmos where we're looking for aliens and not seeing them. But it is still a big factor that we shouldn't ignore. Same as how in other universes a planet might be habitable all the way to its core, not its thin surface, and thus might be vastly more likely to have life emerge, with all the extra places it might be able to pop up at. And with so much more room to grow in, diversification and evolution might happen much faster. Much on smaller or cooler worlds, we would expect evolution to take longer, potentially orders of magnitude longer. This balancing act isn't just for processes like fusion either. How tall a planet can erupt a volcano is based on how strong its gravity is. How fast its tectonic and geological cycles go is also strongly impacted by gravity, as are our tidal effects from the sun and moon. In many cases we can't say by how much, but let's go over some of the major candidates and talk about shifts. How a planet a bit less massive or more or less dense, might differ in habitability and stability. We have quite a few ways minor shifts in gravity might limit if a world was livable and if it stayed that way, but atmospheric retention is a good place to start. Earth is already in at least its third atmosphere and is constantly losing more of it. Gravity helps hold that atmosphere there, but there's leakage. When we get to magnetic fields in a moment, we'll see that loss is prevented as much by our magnetosphere as our gravity, and Venus is only 81.5% Earth's mass, has 90.4% of our surface gravity, and is closer to the Sun and hotter, meaning it gets more solar wind than us, the main source of atmospheric stripping, and is also much hotter, meaning the particles in the planet's atmosphere are moving much faster and need less of a push to get free, all the more so with weaker gravity. Nonetheless, Venus's atmosphere is 93 times more massive than Earth's, so we want to be careful saying a planet can't be much smaller than Earth and keep an atmosphere. That said, Venus loses atmosphere faster than Earth does, and is also very low on hydrogen, the most abundant element in the universe, and also the one that leaks fastest from a planet, with the arguable exception of helium since it doesn't bond anything molecularly, and the isotope helium-3 is especially fast to leave. It's the weight or mass of a molecule, not the atomic mass of any of its individual atoms, that controls how fast a molecule moves at a given temperature, and how much speed it gets from a collision and momentum exchange, much as hitting a car with a cannonball is going to shove it more than hitting a larger truck. As a result, Earth's only helium is from alpha particles slowly drifting up from uranium decaying our planetary core that gather some electrons on the way, and it doesn't stay long, whereas hydrogen bonds well to water. As long as a planet has liquid water on its surface, it's going to have a significant atmosphere too. It can freeze or sink down below ground, as it may have on Mars, but if it remains liquid water on the surface, it will evaporate into a gas as an atmosphere, and the lower the pressure, the faster it evaporates, so a planet can't get too low on atmosphere while it has oceans. But while water vapor is in the air, it can get struck by high-energy radiation, which is good for life down on the surface as it acts as a radiation shield for us. But that can break a hydrogen off the water molecule where it can float around, either rebonding to some other hydroxyl molecule, one hydrogen and one oxygen, or bonding to some other gas there, or finding and bonding to another lone hydrogen atom to form a diatomic hydrogen molecule. It might be jettisoned free by whatever split it too, but otherwise that diatomic hydrogen will float up toward the upper atmosphere, and there it can get broken up again. And way up at the top of the atmosphere it's very thin, so it doesn't have a lot of other particles to collide with, and slow any momentum it got. So sometimes lone hydrogen will get struck by a very high energy particle at the right angle to shove it into space, and other times it will get hit by many without being slowed by some other collision, and then off into space it goes. This is a statistical process and happens way easier on planets that are hotter, are less massive, or are closer to their sun, or around a more volatile sun that sends out more solar wind. Solar wind itself is mostly hydrogen escaping the sun, and at speeds any spaceship we ever made would envy. Thankfully for us, the solar wind coming out the sun's equator is slower, 300 to 500 kilometers or 200 to 300 miles per second, versus what tends to come out the coronal holes, cooler and less dense regions most often found near the sun's poles and going 500 to 800 kilometers or 300 to 500 miles per second. This is one of the reasons why we envision doing star lifting off the polar regions of a star, less work, but that's a different topic. And the orbital velocity of Earth is again just 8 kilometers or 5 miles per second, 8% of what the solar wind moves at. Once out beyond that, they are still gravitationally bound to Earth, but will just keep sucking up high-speed particle collisions till they get pushed clear. And one solar wind particle moving dozens of times Earth's escape velocity and carrying around 1,000 times the kinetic energy needed to escape the gravity well can strike another atom and give it plenty of energy to leave too. This happens exponentially less with heavier particles, hence why Venus has tons of nitrogen and carbon and oxygen in its atmosphere, but virtually no hydrogen. All four of those make up 97.5% of the atoms in your body, with hydrogen outnumbering the other three combined, even if it's only about a tenth of our mass, being just one nucleon, where those other three have 12 to 16 normally, ignoring isotopes. Thus we need hydrogen, and Venus might have a lot of air, but it doesn't have much hydrogen, which is why we still talk about lower mass planets losing their atmosphere in spite of Venus. It really is possible that if Earth were even a few percent less massive, it would have lost too much hydrogen by now, and when we talk about Earth losing its atmosphere and oceans sometime in the next billion years or so, this is from an escalating loss of hydrogen. As the thinner an atmosphere gets, the more quickly it evaporates. Less particles for another to bump into to shed some excess speed it might have gotten from a high-energy collision before it escapes a planet. As to why, that comes down to stability. Atmospheres change with time, and you've probably heard how we used to have little oxygen, but it accumulated as a waste product of life, and did it slow enough to allow life to adapt to use it instead. If a planet's atmosphere changes too fast, especially as a drop-off, this would tend to kill life, but over time a planet with an atmosphere would tend to lose it, and faster than initially. See, the sun warms a bit, stars get warmer as they age long before they go red giant, and emit more solar wind when it does this, and this will erode away our atmosphere left to itself. We could block this with some solar shades at our L1 Lagrange point and some solar-powered magnetic deflectors, letting us live here till at least the red giant phase 4.5 billion years from now, but that requires technology. Not very advanced technology actually, only stuff we could build right now, just a lot of it, but obviously any planet that hasn't got intelligent life is going to be on a doomed path at this point, and the ecosystem will get weaker and smaller as the atmosphere and oceans leave. We could do a whole episode on this, and indeed it is the Nebula exclusive for January 2025, so we'll save it for then, but the other side of this coin is that a planet with stronger gravity also has a problem. If that hydrogen can't escape as easily, then it will bond with things like oxygen, which is very abundant, and make water. Now you have a planet that probably began with more hydrogen anyway, as a raw total, and kept a lot more of it, and isn't really that much bigger in terms of surface area to cover. So it's got deeper seas, and when volcanoes erupt to form land, they have to reach a lot higher to get to the surface of the sea, and they are fighting a lot more gravity to get up there. Volcanoes on lower mass planets, or strikes from asteroids, can also blow away mass into space more easily, and less so of course for higher gravity ones. Here, when a mountain emerging from the ocean gets rained on, the water hits harder from the extra gravity, as raindrops have a higher terminal velocity in higher gravity, though a lower one in thicker air. But thicker air also erodes that mountain as the storms by faster, and every raindrop whacking in now is more likely to knock a grain of sand or rock free, which rolls down with more force under gravity. Avalanches happen easier, mountains have to be wider and shorter, and wear down into the sea even faster, so a planet much bigger than Earth might never get any surface land. And this doesn't just mean only aquatic species, as you don't really get much life at all if you don't have sunlight hitting a patch of water that also has a lot of nutrient in it, which won't happen if it's all miles deep. Virtually all Earth's biomass is on land, and almost all the remainder is right on the coast. So ocean plants don't mean dolphin people, they mean tiny ecosystems hanging around thermal vents deep below on the sea bottom. This might not need to be much more massive than Earth, indeed we might be over the line ourselves. We don't know much about our early planet honestly, we talked about that more in our Primordial Planets episode earlier this year, but we know it was very hot and may not have had much atmosphere, especially hydrogen at that point. It may be that all big planets in or around our mass start low on hydrogen and recollect it by comets, in which case higher mass helps with that too. Bigger planet, more collisions. But we believe early Earth got whacked by something of a dwarf planet to even Mars' mass, and that would have removed any atmosphere we had, and seas. Some may have fallen back down afterward from orbit, but hydrogen would be a lot less likely than other elements in that debris disk to have fallen back down or formed into the moon. Without knowing those conditions better, we don't know that Earth might not have had too much hydrogen from the outset, and lucked out to be hit by another planet. If so, it might be Earth was already too big to have dry surface land and an atmosphere thin enough for sunlight to reach it. But that only a planet our mass or larger could have kept that replacement atmosphere long enough for life to emerge, transition to an oxygen-fueled existence, and kept that atmosphere and our seas long enough to permit you and I to contemplate ways to protect the planet from losing its seas and sky to our increasingly hot sun, which also gets hotter faster when more massive. So our G2 sun not only has a longer lifespan than G1 or G0 or any F, A, B, or O-type stars, it also has a slower transition rate. I would be very dubious of any star more massive than an F7, mass 1.15 times our Sun, about twice as bright, and bound to live 5 to 7 billion years, could ever get life on it long enough to get complex, and in large part because those bigger stars are hotter, giving off more solar wind at higher speeds, and they heat up faster, and even F8 or F9 or maybe even G0 and G1, the classes just a bit bigger than our Sun, might be too much. On the flip side, most stars are smaller than our Sun and will live longer and stay stable longer. We could argue that some change is needed, maybe you need to warm up faster, but that's a hard sell to me, so I don't think any G-type star has a problem. The vastly more abundant and long-lived K-type orange dwarfs probably don't either, though red dwarfs, the coolest, longest-lived, and most common type of star, have problems all their own we discussed in their own episode like colonizing red dwarfs. Gravity also affects the internal dynamics of a planet, including tectonic activity. Plate tectonics help regulate the carbon cycle and maintain a stable climate over geological timescales, both of which are critical for life. A planet too small, with weaker gravity, may not sustain tectonic activity, while stronger gravity may lead to excessive volcanism or other geological hazards. Indeed, we suspect this might be Venus's problem, but there is much speculation and not much evidence where it is concerned, sadly. Planetary composition is also going to be influenced by gravity and its ability to attract and retain heavy elements such as metals, which are essential for core formation, magnetic field generation, and even biological processes. Planets with too weak gravity may lack sufficient heavy elements, impacting habitability and the formation of protective magnetic fields. This too is one of those areas which we still have a lot of question marks on though, and a magnetic field is the key to atmospheric retention, at least for Earth. The presence of a magnetic field, which is driven by the planet's core and influenced by gravity, is crucial for protecting a planet from solar and cosmic radiation. A stable magnetic field shields the atmosphere from being stripped away by stellar winds and cosmic rays, as is the case on Earth. Those incoming solar wind particles are mostly bare hydrogen, thus a charged particle that a magnetic field can deflect. They can also bounce hydrogen back down that got into space but hasn't leaked out yet. Without sufficient gravity to maintain tectonic or core activity, the planet may not generate such a field. Mass also controls orbital stability around a star and if they can capture moons, and many other factors. But gravity's role goes beyond these early Fermi Paradox filters or raw retention of sea and sky. The strength of gravity affects the physiology of potential life forms. In lower gravity environments, life might evolve to have lighter structures, while stronger gravity might favor denser, sturdier organisms. Extreme gravitational conditions could either limit the evolution of life or require significant biological adaptations to cope. This is a good point to wrap up on, because while a lower gravity planet might be able to permit much bigger organisms, taller trees, and huger animals that can more easily afford a big brain, assuming their planet kept its seas and sky, things evolving on higher gravity planets might not be able to afford much size. Too much energy needed to move, too big of muscles required to move limbs that need thicker and denser skeletons. So not only might a bigger planet not have much surface land, or any, or too thick an atmosphere to allow good photosynthesis, it might be that gravity is also just too high to let some creature emerge onto land and not be crushed by its own skeleton, or be too clumsy and heavy to forage for food. Though the reverse case, lower gravity and feather-like critters and mile-high trees that might develop certainly is an option, and a wonderful one to close out on, if their plants can avoid becoming a barren wasteland anyway, by leaking out their atmosphere. That's the problem with gravity and life. It might be even just a bit more is too much, and as mentioned earlier, Earth might itself have too much and just lucked out to get half obliterated when the moon formed, while a planet even a bit smaller than us might have dried up into a barren Martian environment before life got abundant and diverse enough to adapt or spawn some clever apes. Those clever apes might save that planet, or even find some neat ways to use gravity-based technologies, which we'll look at more this winter, but they can't do that if the planet dies before they live. Like I said at the beginning though, that's the thing about gravity. It's awesome and useful, but life forms like you or I can't trust gravity, because unless you're the sea or sky, it will always let you down in the end. Gravity is one of the most difficult aspects of space travel, and as we saw today, it may play a huge role in which worlds can support life. But we also need to consider supporting life off of planets. Or we might grow food in space for people living there, or even send it down on ships or space elevators from orbital farms to hungry planets. In this month's Nebula exclusive, we'll be examining those orbital farms. If you didn't know, Nebula, the largest creator-owned streaming service, has tons of extra content from myself and many other creators, including a new, full-length episode of SFIA like Orbital Farms that we release on the first day of every month. And every episode of this show also airs on Nebula a few days early and ad-free, no random commercials or built-in ads like this one. Using my code, IsaacArthur, you can get 40% off and join for about $3 a month, about the price of the drink or snack you've been enjoying during the episode. We also now have lifetime memberships and gift cards available to let you share Nebula with friends and family. When you sign up at my link, go.nebula.tv/IsaacArthur, and use my code, IsaacArthur, you not only get access to all the great stuff Nebula offers, like Orbital Farms, you'll also be directly supporting this show. This weekend, Sunday, November 24th, we'll be talking about how ultra-relativistic spaceships might be built and function under known science, and just how close to light speed we can get. Then we'll close out the month with a return to our Megastructure series to discuss the Stanford Torus space habitat. and after that, we'll head in November to look at building biospheres on new planets and inside space habitats like the Stanford Torus. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show by becoming a member here on YouTube or at Patreon, or check out other ways to help at isaacarthur.net. Until next time, thanks for watching, and have a great week.